The Earth is taking us on the ride of our lives, hurtling through space in ways we never imagined.
The Earth is extremely dynamic. It is spinning on its axis, it's whirling about the sun, it's corkscrewing throughout this galaxy. It's just never a dull moment.
It's like doing a waltz on top of a carousel that's on top of a high-speed train.
Now, we're unlocking the secrets of our planet's voyage and discovering that Earth's journey affects us all.
We see evidence of this motion everywhere we look, not just in the motions of objects in the sky, but in the land and the seas themselves.
Life on Earth wouldn't be the same if we didn't find ourselves in this dramatic environment in space.
But the ride can be dangerous, plunging our planet into the deep freeze, putting us in the path of supernova, pulling Earth and our entire galaxy toward the unknown.
The galaxy's traveling through space. Where is it going? It's an area of really cosmic mystery.
So strap in for Earth's cosmic journey. We are Earth's passengers as our home planet travels through the cosmos. To us, everything seems calm. Nothing could be further from the truth.
Contrary to what you might think just based on your everyday experience, the Earth is actually hurtling through space at amazing speeds in a lot of different ways. Even just the motion of the stars through the sky at night gives you a clue that the Earth is not sitting still.
The Earth is spinning at every moment, and we can see this most clearly in the fact that we have day and night.
We might not think about it, but our lives are tuned to Earth's journey as it spins through space.
There's really nothing more basic to us than that cycle of day and night, that 24-hour cycle.
All of life on Earth evolved with a day-night cycle. So it's ingrained into every organism on this planet.
Life evolved in lockstep with Earth's spinning motion. But in the ocean, corals take things a step further. By keeping a record of every planetary turn.
They have a daily cycle which creates a deposit almost like a tree ring, but instead of it being once a year, it's once a day.
So you look at a bunch of tree rings, you can count the number of years the tree was alive. Corals record not just the yearly cycle, but the daily cycle of night and day. These are recorded in these little growth bands in the coral.
By counting the coral's growth bands, we can work out the number of days in a year. But when we look at ancient fossilized coral, we discover something strange.
We can look at fossils of corals that are hundreds of million years old, and if we do that, we find that the year is not 365 days long. It's more like 420 days long.
The length of a year is how long Earth takes to orbit the sun. Hundreds of millions of years ago, it took our planet the same amount of time to orbit as today. But somehow, there were 420 days. How is this possible?
We all know that the rate of the spin of the Earth today is 24 hours, but it hasn't always been that way.
When the ancient corals were alive, there were 420 days in one Earth year, meaning a day was just 21 hours long. To find out how this was possible, we need to go back to the start of Earth's cosmic journey. $4.6 billion years ago, our planet traveled a dangerous path through a chaotic and violent solar system. Collisions were frequent. One giant impact set our planet spinning rapidly. And formed the moon.
The rotation of the Earth has always been wrapped up with the moon, and billions of years ago in a very, very dramatic way. The moon was formed when another planet that we often call Theia hit the Earth. And what was left over after that collision was a superheated donut of vaporized rock around the Earth called a synestia.
The donut of rock span at 10,000 miles an hour and swirled through space for hundreds of years. Slowly, the cloud of vaporized rock began to cool. The moon formed in orbit around a rotating and accelerating molten Earth.
Using the ice skater analogy, when the object is larger, it spins a little more slowly, and as it contracts, it spins faster to conserve angular momentum. And so as the hot rock vapor cools and rains out onto the central planet, it will spin faster and faster. Going all the way back to the time that the moon formed, the Earth may have had a day as short as 2.5 hours.
As the Earth continued on its path through the early solar system, our planet cooled and the surface became solid. But the violence wasn't over.
The young Earth was bombarded in the early days of the solar system. And when these rocks hit the Earth, they almost never hit directly on, they'd hit at an angle.
With each collision, it adds a little bit more momentum and a little bit more spin to the Earth. The added spin that you get is kind of like a merry-go-round. You can imagine with each kid that pushes and jumps on the merry-go-round, you have greater spin.
As our planet journeyed on, asteroid impacts set the young Earth spinning 12 times faster than it does today. Our planet's rotational speed has huge consequences for life.
On Earth, the spin of our planet actually has an effect on our weather. With a shorter day, one of the effects that might have been apparent on Earth at that time was more storms developing.
A phenomena still in action today drove these powerful ancient storms. We call it the Coriolis effect.
The Earth's spin creates phenomena in Earth's atmosphere and oceans. This determines patterns of circulation in combination with the heat energy from the sun.
The rotation of the Earth matched with solar heating, especially at the equator, causes air to rise up and then also sort of to move sideways and sets up spin.
As we spin around the sun, Earth's rotation creates our global wind patterns. But the winds on the early Earth would have been far more extreme.
When we think about what that might have done to the Earth environment, we can actually look to another planet. Jupiter is spinning incredibly fast, and it has some crazy storms.
We notice that there's lots and lots of motion of the atmosphere and also myriad cyclonic storms that have risen up.
The largest and most powerful is the Great Red Spot. A storm twice the width of Earth, with wind speeds up to 400 miles per hour.
The storms that we observe on Jupiter are absolutely insane. They are huge, they are powerful, they are probably very destructive. So that gives us a sense of what the storms might be like on Earth if Earth had a faster rotation period.
As the young Earth continued its journey, the planet's rotation whipped up furious planet-wide storms. A fast spin would have been disastrous for any life.
The storms would have been so big, it's hard to say if life would have evolved at all.
Fortunately for humankind, Earth has a traveling companion, the Moon, and it helps slow our planet's spin.
What happened next was kind of a wonderful gravitational dance between these two bodies. As they were spinning, they were also interacting with each other.
The Moon's gravity pulled on Earth's oceans, generating tidal bulges.
Material was moving in and out of the tidal bulges as they spun, and this creates friction and a kind of drag that actually slowed down the rotation.
The tides also helped create life. Giant tides swept nutrients from the land into the oceans for the first time. A primordial soup began brewing, and life arose. As Earth's spin continued to slow down, life spread across the planet. But our planet's spin is just one part of our cosmic ride.
Realizing how complicated our larger environment in the universe is a wonderful thing. There are so many things that affect the orbit of the Earth, the tilt of the Earth, things that affect our climate.
Clues to the Earth's space voyage are hidden right across the world. Could our planet's wild ride explain how one of the driest places on the planet was once wet? The Sahara Desert, dry, dusty, and desolate. But hidden deep in a desert cave is a clue that thousands of years ago, the Sahara was a lush, green paradise.
Archaeologists have unearthed rock art which clearly depicts humans and animals swimming in lakes. And by looking at satellite images, we can trace out the outlines of ancient river valleys.
The Earth's fast rotation influenced our planet's ancient weather patterns. Could another motion have changed the desert climate? To unravel the mystery, we need to rewind the clock 4.6 billion years. To when the infant solar system was a planetary shooting gallery. And the Earth spanned through the solar system with a slight tilt.
Earlier on, before the formation of the Moon, the Earth didn't have much of a tilt, and the impact knocked us completely out of whack to about 80 degrees.
Our planet might have continued its journey tilted right over, but the Moon's gravity pulled us upright. Just not completely.
The Moon is not quite in the equatorial plane of the Earth. It's above the equatorial plane, and it pulls the Earth's axis into a 23.5 degree tilt.
If we didn't have the tilt to about 23 degrees, then we wouldn't have the seasons, and these seasons drive a lot of the crops and the growth and the ability to survive all across the globe.
But the ancient greening of the Sahara can't be explained by the changing seasons. Another planetary motion must be in play. A clue is found in the sky. The North Star.
Right now, the Earth's axis is pointed towards a star in the sky called the North Star, Polaris. We've actually named it after the fact that the North Pole of the Earth points toward it in the sky.
But Polaris hasn't always been the North Star.
5,000 years ago, it was a totally different star. It was Thuban, which is in Draco, a different constellation. Sometime in the future, it'll be Vega, the brightest star in the constellation Lyra. So the North Star actually changes because the North Pole's position in the sky changes.
The changing pole star is evidence that Earth is wobbling through space. It's a process called precession, something that also affects spinning tops.
If you take a top and let it spin really rapidly and poke it, the axis of rotation will spin around like this. And it's much slower than the actual spin of the object. That is precession, this circle that the axis is making. This happens to the Earth as well.
A cosmic poke caused Earth's space wobble. But what has the power to poke a planet? Once again, gravity is the key. This time, Earth's gravitational interactions with the moon and sun.
These forces are that poke on the spinning Earth, and that's what makes the Earth's axis spin in precession. And it takes about 20,000 years to make a complete circle once.
As the Earth continues its journey around the sun, this wobbling motion changes the planet's climate dramatically. When the Earth's North Pole leans toward the sun, Northern Hemisphere summers are sunnier, with unexpected consequences for the Sahara.
It turns out at times when the climate in the Sahara gets more sunshine, that warms the climate up and the winds come in from the ocean. It's called the monsoon effect, and brings water, rain into the Sahara where now it's dry.
This pattern of wet and dry climates that produce this 20,000-year cycle is what we see in the Sahara, where at times of strong monsoon, the Sahara is wetter, a green Sahara.
10,000 years ago, as the Earth wobbled through space, monsoons were unleashed, turning the desert green. Humans migrated to the newly lush Sahara and created the cave paintings we see today. But this wasn't the first time humans crossed a green Sahara.
A dry Sahara would have presented an insurmountable barrier to our ancestors from migrating out of Africa. But during one of these cycles, when the Sahara was green, it would have been a corridor that we could have migrated and dispersed on.
Earth's wobbling motion through space transformed the Sahara and the fate of humankind. But there are more cosmic forces affecting our journey through the universe.
The Earth's orbit around the sun is another thing that seems very, very solid. We understand how it works. But everything in the universe is a delicately tuned dance of gravity, and things can change even from tiny little influences.
As our planet hurtles through space, other worlds influence our path. Could a planetary bully push Earth's climate to the extreme? Earth carries us on a wild journey through the cosmos. And clues to the effects of this trip are hiding in our own backyard. In New York City, amongst the buildings and traffic, we find moraines, rocks left behind by retreating glaciers. 18,000 years ago, a sheet of ice taller than any skyscraper covered Manhattan. Ice ages have struck regularly throughout Earth's history, putting our planet in a deep freeze.
There was a period in Earth's history several 100 million years ago, the snowball Earth period. We went through a very extreme glaciation, if you will, a very extreme ice age, where we think perhaps the entire Earth was covered in an ice sheet.
The trigger: Earth's orbital dance around the sun.
We tend to think of ourselves sitting relatively stationary on the Earth. It's pretty comforting, actually. But we're orbiting the sun at about 66,000 miles per hour.
Every day, Earth travels over 1.6 million miles on its journey around the sun. This orbit isn't always completely round.
Earth is generally going around the sun in more or less a circular orbit. But over time, the massaging of this orbit from the sun, from the moon, on the Earth's orbit causes the orbit of the Earth to change. So that sometimes it's an ellipse, sometimes it's more of a circle. Right now on the Earth, we're in kind of the most circular time in the orbit. So that means the summers are relatively mild and the winters are relatively mild. But imagine not that long ago in the past, it could have been really dramatically different. When the Earth is a little bit closer to the sun, maybe you have a really severe summer, and then on the other side of the orbit, you're a little farther away from the sun than normal, so you have a really severe winter.
Our environment is very, very sensitive to these things. And when the Earth's orbit is stretched out, that can actually trigger an ice age.
Our planet's 100,000-year orbital cycle caused the ice age that buried New York. And ice ages have had a big impact on human history. 15,000 years ago, plunging temperatures locked water away in glaciers and ice caps. Sea levels dropped, creating land bridges between continents. Humans migrated from Asia to America by foot. America was inhabited for the first time. May 2018, scientists revealed a whole new dynamic to Earth's journey. Every 405,000 years, our planet's orbital voyage stretches to the extreme, and Earth's planetary neighbors are to blame.
Because Jupiter is the most massive planet in our solar system, it is in many ways the bully on the playground, right? Its dynamics, its gravity, sculpts a lot of the dynamics of the solar system.
It actually tugs and pulls on the orbit of the Earth itself. It's responsible for some of the very changes that drive our climatic cycle here on our planet.
Jupiter isn't the only bully in the playground.
Venus is a fairly big planet about the size of the Earth, and it also comes closest to us in its orbit. So these two planets put just a little tiny elongation onto our Earth's orbit. And as this cycle continues, the more extreme it gets, we can actually notice a temperature difference that happens about once every 405,000 years.
Jupiter and Venus gang up on the Earth gravitationally, pulling Earth's orbit into an even greater ellipse. Our planet's hot weather becomes hotter, and its cold weather gets much colder. Today, we're in a moderate part of the cycle, but in just 60,000 years' time, we could plunge into another deep freeze.
It's a little bit like a cosmic butterfly effect. I mean, even the smallest effects can have, big influence over time.
Earth's orbit around the sun is just part of our far larger cosmic journey. The entire solar system is hurtling around the Milky Way, taking us places we don't want to be.
Sometimes our planet might wander into what's essentially a bad neighborhood.
Could these neighborhoods spell disaster for life on Earth? Over the last 3.7 billion years, a series of extinction events wiped out almost 95% of all species on Earth. Now, research suggests our planet's orbit could be partly to blame. Not Earth's voyage around the sun, our planet's larger and longer journey around the Milky Way.
Our solar system and our sun is shooting through the galaxy at about 537,000 miles per hour around the center of our galaxy. And that center of the galaxy is about 26,000 light years away, so it should take the sun about 230 million years to trace out one full orbit around the center of the galaxy.
Despite racing round the Milky Way at 500,000 miles an hour, Earth has completed less than 20 laps of the galaxy in our planet's entire history. And it turns out, this galactic ride is more complex than it seems.
Now, if you look at the Earth going around the sun, it defines an ellipse, but that's a flat figure. And you'd think, well, the sun probably goes around in a plane as well. And it turns out, not that simple.
Most of the mass of the solar system is concentrated in the sun, so Earth and the other planets smoothly orbit our star. The mass of the Milky Way is spread out unevenly.
That changes the gravity of the galaxy, and so it changes how things move in it. And in fact, if you give something a little bit of an up or down motion, it'll bob up and down as it goes around.
Riding the Earth is almost like riding a carousel. As the sun and the Earth go around the galaxy, the sun also goes up and down like you're on one of those horses with the pole. And so what this can do is take us into different galactic environments.
This bobbing motion takes Earth and the solar system on a 60,000-year journey, up and down through the Milky Way's galactic plane. Our orbit also takes us through different galactic neighborhoods. Today, we're traveling through a calm suburb of the galaxy. But sometimes, things get a little bumpy.
Sometimes our sun and our planet might wander into what's essentially a bad neighborhood. You know, maybe it's an area where there's a lot of star formation going on, where there's a lot of young stars that are very active. Or maybe it's a location where there are dying stars and things are about to get really hot.
The baddest neighborhoods in the galaxy may be the spiral arms. These gas-filled regions orbit the galactic center more slowly than the Earth. So our planet passes through an arm roughly every 150 million years.
These arms are where gas clouds tend to hang out. And if they get compressed, they form a lot of stars. When they form a lot of stars, they make bright blue stars. And they don't last long and they blow up as supernovae. So it's possible that as we're passing through these regions, these are places you might not want to be in. So in the distant past, this may have affected the Earth.
When giant stars go supernova, the star's outer layers blast into space. Along with a shock wave traveling at 25,000 miles per second. Supernova also release cosmic rays. Space bullets that shoot across the galaxy at close to the speed of light.
And you don't want to be exposed to too many of them. But in high enough doses, these things penetrate our cells and damage our DNA, and over the long term can cause really bad damage to human bodies.
As we ride through space, Earth's magnetic field protects us from most cosmic rays. But in 2018, we discovered evidence that a hail of space bullets overwhelmed our planet's magnetic field in the past.
In many ways, we really take for granted how the Earth protects us from space. But there are records that we've actually bounced a little too close to exploding stars.
Sediments in the ocean show that about 2 million years ago, iron-60 was deposited in our oceans. Iron-60 is a radioactive isotope of iron, and there's only one way we know of it being made in the universe, and that is exploding stars.
Around 2.8 million years ago, a supernova exploded just 150 light years from Earth. A few hundred years later, a blizzard of cosmic rays slammed into the Earth, tearing through our magnetic field. These space bullets are a prime suspect in the extinction of over a third of all coastal marine species.
Now, this is not necessarily tied to the Earth passing through one of these spiral arms, but it shows you that being close to a supernova is not necessarily a thing you want to do.
Millions of years in the future, Earth will pass through another spiral arm as our planet continues its journey through the Milky Way. And we will wander into harm's way once again. But supernovas aren't the only cosmic threat linked to Earth's journey through the galaxy. 66 million years ago, a trillion-ton object hit the Earth at 25,000 miles an hour, blowing 5 trillion tons of debris into the sky. This impact wiped out the dinosaurs. And this extinction event wasn't a one-off.
If one looks in the geological record, let's say one looks at the record of life, it turns out that mass extinctions of life, like the dinosaur mass extinction, didn't happen just once. They happen about every 26 or so million years. That's essentially the same cycle.
A controversial theory suggests our galactic orbit is to blame. When the Earth is bobbing through the galactic plane, we run the risk of passing close to other stars. These stars can gravitationally disrupt the solar system around us, including the Oort cloud, a shell of 2 trillion icy bodies loosely bound to the solar system.
One thing that could happen is comets can be sent into the inner solar system, increasing the rate of collisions.
If the comet is big enough, it can cause a mass extinction like the one that happened 66 million years ago.
The death of the dinosaur, along with 70% of all life on Earth, lines up with our passage through the galactic plane. The event killed off the masters of the planet, but allowed the rise of a new creature, mammals, and ultimately us. But there's another part of our journey through space that remains a mystery.
The Earth is spinning like a top on its axis. It's orbiting around the sun. The sun itself is orbiting around the center of the Milky Way, but that's far from it.
The Milky Way is speeding through the universe and we are being dragged along for the ride. The problem is, we can't see where we're going. Could Earth be headed for a galactic crash? Like the craziest theme park ride, we are riding the Earth on a wild journey through the cosmos. Our planet spins, tilts, and wobbles around the solar system, while bobbing like a carousel through the Milky Way.
The dynamics of the Earth moving in the cosmic void is like the most unbelievable journey you could ever imagine. And as you get to larger scales, the motions only become grander and larger and more dynamic.
In 1977, we tried to work out the largest motion of all: the movement of our galaxy through the universe. Clues hide in the cosmic microwave background, a remnant from the birth of the universe.
The cosmic microwave background is the radiation that's left over from the hot Big Bang. The cosmic microwave background is shining in all directions, it's sort of this fixed thing. And if we're moving through it with some speed, we will see that in the light itself. You can measure that, and by measuring that, you can get a sense of how fast we're moving through that space.
By tracking our movement through the universe against a fixed point, we can work out the Milky Way's speed and direction. But in 1977, telescopes weren't the best tools for the job.
During the Cold War, 1977, you have the newly declassified U-2 spy plane, this very high-altitude reconnaissance aircraft. NASA retrofitted one of them with an upward-facing window, and with very sensitive receivers, the spy plane became the first experiment to, for the first time, definitively measure the motion of the galaxy through the universe.
As the U-2 spy plane soared above the Earth, it measured the cosmic microwave background in unprecedented detail. The data revealed that our galaxy races through the universe at 370 miles a second. That's over 1,000,000 miles an hour.
Think of how big a galaxy is. Hundreds of millions of stars, and we're moving at hundreds of miles per second. That's just a tiny bit mind-blowing.
The Milky Way's speed isn't the most alarming part of our galactic journey. From Earth, we can't see in the direction our galaxy is taking us. We're flying blind, our view blocked by the Milky Way itself.
So if you are actually looking through the plane of the galaxy, through the plane of the pancake, your view of the galaxy is obscured by curtains of dust and gas that envelop our solar system.
It's very bright, there's a lot of stars, and our view is blocked by the galaxy itself. So there's a zone directly behind the galaxy as we look towards the galactic center that's really an unknown area. It's a zone we call the zone of avoidance, and it's an area of really cosmic mystery.
Thanks to this mysterious zone, we thought we could be headed for a galactic car crash. Then we had a breakthrough. We used powerful radio telescopes to look through the zone of avoidance for the first time.
One of the nice things about using light that's in the radio is that this kind of light actually can go through pretty dense kinds of gas and stars and allows us to sort of look through things. Using these radio telescopes has given us a glimpse into what lies beyond the zone of avoidance.
Peering through the cloud of cosmic gas, we discovered that our galaxy is just one tiny element in a vast cluster of galaxies. sailing through the cosmos together.
We think that our galaxy, the Milky Way, is part of a much grander cosmic flow of galaxies. And it is part of what may be the Laniakea supercluster of galaxies, this giant cosmic structure filled with potentially thousands of galaxies that is moving together in this beautiful, like, slow-moving river that is sculpted and dictated by gravity itself.
Earth voyages through space along gravitational rivers hundreds of millions of light years long, along with a fleet of 100,000 other galaxies, all moving toward a single point in space, a gravitational drain known as the Great Attractor.
The Great Attractor is the local region of gravity, of strong gravity in this patch of the universe. It's where all the galaxies in this chunk of the universe are flowing towards. At the location of the Great Attractor is a bunch of material, a bunch of gas, a bunch of galaxies, an extremely massive cluster. And over time, more and more galaxies add themselves to this cluster as they continue to join the Great Attractor.
It's unlikely Earth will ever reach the Great Attractor. As we speed towards it, we are heading for a collision after all. Is this how our cosmic journey ends? Earth's voyage across the cosmos has lasted for 4.5 billion years. The big question is, how will our journey finally end? A clue comes from the Milky Way's traveling companion, another galaxy, Andromeda, filled with up to 1 trillion stars that's charting a similar path to us.
The Andromeda Galaxy is another big spiral galaxy, a lot like our Milky Way. And it turns out the two of us are heading for each other.
Andromeda and the Milky Way are currently 2.5 million light years apart, but hurtling towards each other at over 250,000 miles per hour. A collision is inevitable.
Galaxies colliding with each other sounds like science fiction, but the collision of the Andromeda Galaxy and the Milky Way Galaxy will be a spectacular event.
When the Andromeda and Milky Way galaxies collide, it's gonna be a ridiculous light show. The stars don't collide, but the giant clouds of gas do, and that's gonna trigger star formation. So we're gonna have what's known as a starburst galaxy.
When Andromeda finally merges with the Milky Way, all bets are off. All of a sudden, a system of hundreds of billions of stars will be added to our own, and there will be mass chaos. But one thing you can guarantee, there is going to be celestial fireworks.
This could be the biggest light show in history, resulting in the creation of a brand new galaxy.
We will have become one giant galaxy. Call it Milkdromeda, if you will. So we will look very different. Our grand design spiral Milky Way galaxy will have probably transformed itself into an entirely different shape.
The merging galaxies could create a giant elliptical-shaped galaxy, but Earth might not be around to see it.
Billions of stars are going to come careening into our galaxy, very, very easily disrupting the orbit of the Earth. The sun could be thrown out of the galaxy entirely.
As stars, dust, and gas swirl around each other, gravitational interactions could slingshot our solar system out into intergalactic space.
We'll still orbit the sun and everything will be fine, kinda, but it just means we'll see something very different in our sky in 4.6 billion years than we do now.
Our planet could be sent on a whole new intergalactic ride. shot out into the cosmos, away from the new Milkdromeda galaxy.
There's no way of knowing exactly what's going to happen. And in that sense, Journey's End, we'll just have to wait and see.
We might not know the final destination for Earth's cosmic journey, but what an incredible ride it's been so far.
We've had a fantastic journey over the history of Earth's existence. We may not be immediately aware of our motions through the universe, but that doesn't mean they're not there.
Many people think of the Earth as this blue, calm marble in space. But in reality, it's violently ripping around the sun, and the sun is ripping about the galaxy. There's a lot of dynamics happening.
It boggles the mind just to think of what the Earth will have done. The Earth will have actually orbited the sun 10 billion times. It will have spun on its axis like 1 trillion times, and the galaxy is moving through space. Riding the Earth is anything but a boring trip.